Alright class, let's continue with solubility product. We're going to talk about common ion effect and solubility product. You know common ion effect from the buffer chapter. The solubility of a compound goes down based on Le Chatelier principle. Now before I explain this, don't write anything down. Let's do a practice problem to kind of show you the common ion effect, and then we come back to the conceptual after that. Alright, ready for our first practice problem, which also help you to review a little bit? Here is our first problem, part A. What is the molar solubility of lead-2 fluoride? Okay, pause me and do this on your own. Hopefully this should be a piece of cake right now, but don't forget what I taught you. Don't get ahead of yourself. Always write down the basics. It's an equilibrium equation because I have KSP. That means some of the lead-2 fluoride is going to break up into ion. It's going to break up into Pb plus 2 and 2F minus. Yes. And you are going to write down the KSP expression, which is the concentration of lead-2 ion times the concentration of fluoride to the power of 2. Okay, now this is solid. Of course, it's not going to be part of the KSP. Now we said that molar solubility is basically the X. As lead-2 fluoride dissolves, you end up forming lead and you end up forming fluoride. So X and 2X based on the coefficient, right? One of these dissolves, you end up one of these, and you end up forming two of this. Okay, now in this case, the KSP is given to you. I'm just going to plug in KSP, which is 3.7 times 10 to the minus 8. PB is my X, F is my 2X. But I'm still going to square it that because the 2X is a concentration, the X is a concentration, but the formula still calls for you to raise it to the coefficient. I have to still do that. Now, if I do that, what I end up getting, I'm going to end up in 3.7 times 10 to the minus 8 equals, now I get, again, we did this before, but just really quickly again, the 2 goes here, this becomes 4, and this becomes x squared, and then when you multiply everything together, what you end up getting is 4x to the power of 3. Okay, so now if I solve for x, I get 2.1 times 10 to the minus 3, and x is my molar solubility of lead-2 fluoride. So far so good. Okay, now what we're going to do, the part B of this problem. Okay, so here's part B. What is the molar solubility of lead-2 fluoride in a 0.10 molar sodium fluoride? Now, again, and this is the KSP for, I should have mentioned that. This is the KSP again for PbF2. Okay. Now, I know this is a KSP for PbF2 because lead-2 fluoride is my insoluble solid. The same as before, the same as part A. I'm going to write down the equilibrium equation. Now, in this problem, and again, like the same as before, I have minus x, and I have x, and I have 2x. Nothing has changed, right? Also, the same as before, nothing has changed because the KSP is for the insoluble solid, which is lead-2 fluoride. So then it would be the concentration of Pb times the concentration of fluoride to the power of 2. You got this down. Now, the only thing in this question, they ask you that you also have 0.1 molar sodium fluoride in there. You notice because we did it in buffer. When you see that, you go, okay, first of all, sodium fluoride would have 100% dissociation in water, right? To Na plus and F minus. There's no equilibrium. So if I have 0.1 molar of sodium fluoride, it would completely dissociate. I end up with 0.10 molar sodium plus and 0.10 molar fluoride minus. Okay, it would completely dissociate, and I would end up having those together. All right, now this is a common ion effect problem. Why is this a common ion effect problem? You totally got this because check this out. What do I have? I have fluoride. Sodium doesn't really do anything for me because if I have the fluoride, and guess what? I have fluoride in a part of my equation. So it's a common ion effect. It's a common ion effect because I already have some of this in the solution when I add the lead 2 fluoride in it. So my common ion effect solution. Okay, so at the very beginning, before this is going on, I have 0.10 molar of fluoride already in the solution. Okay, again, this is exactly like the buffer problems we did. So KSP, which is 3.7 times 10 to the minus 8 is equal. Lead is my X. Now, what is fluoride? Fluoride is 0.10 plus 2x, then to the power of 2. If you remember, we did this with a buffer. We had the ice table, and then at the ice table, when we had a buffer, we had some of this and then some of the other one in the equation. The same thing. Now here I have my lead 2 fluoride is what's doing the equilibrium, but I have already sodium fluoride in the solution. Sodium doesn't do anything, but the fluoride, because sodium fluoride would be 100% dissociated into sodium plus F minus. F minus, whoa, I have that in the equation, don't I? So that's the common ion effect. So then I can do this now. You can assume X is 0 here. You can assume X is 0 because it's very, very small compared to 0.1. That makes your life a little bit better. So then it just becomes X times 0.10 to the power of 2. Don't forget that. So if I solve for X, I get 3.7 times 10 to the minus 6 for molar solubility of lead 2 fluoride. Okay. Now, let's see what happened. This was the molar solubility of lead 2 fluoride. And then when I had a common ion effect, what happened to the molar solubility? The molar solubility went down. Does that make sense conceptually? Let's talk about it conceptually, if that makes sense or not. Let's talk about it if it makes sense conceptually. So, I had lead 2 fluoride. I have this equilibrium going on. Now, what's going on here? I have some of this already in the solution, right? If I have some of this in the solution, which way would the equilibrium shift to balance it out? The equilibrium will shift this one because the equilibrium goes, oh no, now I have a lot of this. I need to shift this one to reach the equilibrium. So when you do this, when you add in the common ion, it shifts to the left. Now, if it shifts to the left, that means less of lead 2 fluoride will be dissolving. That means less of the lead 2 fluoride will be dissolving. So that's what I expected. I expected the molar solubility to be less. I expected the molar solubility to go down, and it gone down significantly. It was 2.1 times 10 to the minus 3. Now it's minus 6. It went down again because of common ion effect. That's what I expected because I add some of this, so it's gonna shift to the reactant. So I have less of this ionizing into lead and fluoride. So far, so good. Okay, let's do one more practice problem. All right, our next practice problem. This is our next practice problem. Again, pause me and then do this, and then watch the video again. So calcium hydroxide is our insoluble solid, right? But we know some of it will dissolve. So I'm going to have an equilibrium. It's going to break up into ions, calcium, and then 2OH minus, okay? And again, the same as before, don't forget the KSP would be the concentration of calcium times the concentration of hydroxide to the power of 2. And then this is minus X, this is X, and this is 2X. Okay, now, do we have the KSP? We do have the KSP is given to us, 1.3 times 10 to the minus 6. Calcium is X. My hydroxide is 2X. Again, don't forget, the 2X is the concentration, but then I have to do it to the power of 2 because that's part of the formula. Now, what I end up getting then is 4x to the power of 3. If I solve for x, what I end up getting is 6.9 times 10 to the minus third. Again, that is my molar solubility. This is my molar solubility. Okay. Now, the next question. Again, it asks you to calculate the solubility of calcium hydroxide, but this time in the solution is also some calcium nitrate. Now, you notice calcium nitrate is 100% soluble in water. So all the nitrates are 100% soluble. So you end up with calcium and you end up with 2 nitrate going up. So far so good. Okay. Now, here's the thing. What kind of question do I have here? I'm hoping you're yelling that right now I have a common ion question. The nitrate doesn't do any good because the nitrate is not part of the equation whatsoever. But what is part of the equation? The calcium is part of the equation. The calcium is part of the equation, so I have a common ion effect problem. I have a common ion problem. So far so good. Okay. Again, I'm going to rewrite this to make sure we are on the same page. So I have calcium hydroxide. It goes back and forth to the calcium plus 2 OH minus. Again, the same as before. This is minus x and 2x. Except I have a common ion effect. So what I already have some of the calcium in the solution, right? How much of it do I have? Again, don't forget your Chem 1A stuff. That's what's going to come back to you. So I had, don't do that. I have 0.10 molar calcium hydroxide. When this breaks up, I end up with 0.10 molar calcium, but 0.20 molar nitrate. I know nitrate is not, I'm not going to use a nitrate, but I just wanted to remind you that don't forget that you still have to use a mole ratio here. But again, nitrate, I'm not going to do anything with it because it's not part of this, but calcium is. And I have 0.10 molar of calcium in this solution before I start. Oh, I did not just do that right. Hold on a second. This is my calcium. I got a little too excited. I don't have any of that at the beginning, but I do have some of the calcium already in the solution. Okay, and this is kind of like an ice table if you want to look at it. I can even write it as an ice table if that would makes it a little bit easier for you guys to understand. This is not going to be, this calcium hydroxide is solid, not going to be even part of it. This is 0.10 plus x, and this is my 2x, and this is nothing again because solid is not part of the equilibrium. So my KSP is going to be calcium hydroxide times calcium plus 2 times hydroxide to the power of 2. So my calcium is going to be 0.10 plus x. Hydroxide is 2x to the power of 2. Don't forget that. And the KSP was also given. Again, I know I keep repeating myself. Just remember, these are the concentration. You're going to plug those in for the concentration, but the formula calls for you raising it to the power of the coefficient. Don't forget that. Okay. Now, can I assume some things are 0? Absolutely. I can assume this is 0 because whatever that number is so much smaller than 0.1. So if I do that, what do I end up getting? So 1.3 times 10 to the minus 6, which is my KSP, equal 0.10 times 4x squared. I factor it out. So 1.3 times 10 to the minus 6 is equal 0.40 x squared. What I get for x is 1.8 times 10 to the minus 3 molar. Okay. Now, what happened to the molar solubility? Is that what you expected? You expected it to go down. Did it go down? It did go down. Not by whole much, but it did go down. This was 6.9 times 10 to the minus 3. Now This is 1.8 times 10 to the minus 3. The solubility went down. Why did the solubility go down? Because of the common ion effect. Because if you add one of these common ions, you expect it to shift to the left, so you have more of this together as a solid and less of the ions. So again, common ion effect. Because of the common ion effect, it makes them solubility. Common ion effect is that the solubility went down. The solubility decreased. So common ion effect makes the solubility decrease. Why? Because of the Chatelier principle. I add one of these, it shifts equilibrium to the left. Okay, nice job. So that was our common ion effect and KSP. I will talk to you guys next time.